let's just dive right into this explainer. Today, we're taking a grand tour, and I mean a truly grand tour. We're going to start with the foundational rules of reality, zoom all the way down to the absolute tiniest quantum particles, and then scale right back up to the massive interdependent systems that govern our everyday lives. Ultimately, our goal here is to summarize the main concept that bridges the microscopic world to the macroscopic world, showing exactly how literally everything is deeply interconnected. To make sense of all this, we'll be using a deliberate zoom-in, zoom-out framework today. We'll start with the basic rules of science, peek inside the atom, bend our minds a bit in the quantum realm, explore how chemistry builds our daily life, and finally, look at massive interdependent systems. Section 1. The Rules of Science, the foundations of our physical world. So I want to kick things off with a question, mostly because this is one of the biggest misconceptions out there. When you watch the news or you're just chatting with a friend, you'll probably hear someone say, well, that's just a theory. But do you know the actual difference between a theory and a hypothesis in the scientific world? People use them totally interchangeably in everyday conversation, but in science, they are vastly different. A hypothesis is basically an educated prediction. It's an attempt to explain something based on what we currently know. But a theory is a set of fundamental ideas that are consistent with all known observations. It's widely accepted because of overwhelming, repeatable evidence. So when science calls something a theory, they aren't just guessing. It is a rigorously tested foundation. Moving from scientific thought over to physical laws, we hit our very first building block of physical motion, Newton's second law. You've probably seen this famous equation, F equals ma. Net force equals mass times acceleration. Put simply, if an object is accelerating, there is absolutely a net force acting on it. And logically, you're going to need a much greater force to accelerate a larger mass than a smaller one. This rule actually applies beautifully even at the microscopic level. Picture a molecule moving at a perfectly constant speed, hitting a wall, and then bouncing back. It didn't change its speed, right? But because it changed its direction, its velocity changed. Therefore, it actually experienced an average acceleration, and a pretty significant one at that. It's a great reminder that acceleration isn't just about stepping on the gas. It's about any change in velocity. And right here, we can bust another really common myth. Does negative acceleration always mean an object is slowing down? The answer is a definitive no. It depends entirely on which direction you define as positive. Say you define moving to the left as a negative direction. If an object starts speeding up as it moves left, its velocity is becoming more negative. That means it has a negative acceleration, even though it is physically speeding up. Wild, right? Another absolute rule of our physical world relates to energy. Whether it's a golf ball flying through the air or your car's engine burning fuel to merge onto the highway, energy is constantly being transferred. And the golden rule is this: when energy is transferred or converted into another form, it absolutely must eventually appear as work or heat or some combination of the two. Section 2. Inside the atom, scaling down to the microscopic building blocks. Our understanding of the atom evolved incredibly fast. In 1803, John Dalton proposed that all matter is made of tiny, indivisible particles that just rearrange themselves during chemical reactions. Fast forward to 1911, and Ernest Rutherford realized the atom wasn't some solid block. It actually had a super dense, positively charged nucleus surrounded by mostly empty space. Just 2 years later, Niels Bohr added that electrons absorb and emit specific, quantized amounts of energy as they jump between discrete orbits. It's amazing how quickly science builds on itself. Now, what's truly mind-blowing here is the sheer scale of that atomic structure Rutherford discovered. When you look at a 3D model of a molecule, it looks completely solid. But the actual space where electrons move about is at least 1,000 times larger than the diameter of the nucleus itself. Think of it like this. If the nucleus was a tiny marble sitting on the 50-yard line of a massive football stadium, the electrons would be buzzing around way up in the highest bleachers. That means you, me, the chair you're sitting on, we are all primarily made of empty space. Section 3. The quantum realm. When classical rules no longer apply. As if being mostly empty space wasn't weird enough, let's zoom in even further to the absolutely mind-bending reality of the quantum realm, where the classical rules we just talked about start to completely break down. The crucial thing to grasp here is the superposition principle. Our source text puts it perfectly. Whenever the photon is in one state, it can always be considered to be partly in each of the two states. Wait, what does that actually mean? Well, in the quantum realm, a particle doesn't just pick one path. It exists in a blurred, indeterminate combination of possible states, all at once. We actually see this proven in the modern-day double-slit experiment. When a photon enters a beam splitter, exactly half the time it should go left and half the time it should go straight. But because of superposition, until that photon is physically measured by a detector, it exists in a combination of both states. It is effectively taking multiple paths at the exact same time. It is literally a completely different rulebook down at the scale. Section 4, Chemistry in Daily Life. Building back up to the macroscopic world. Okay, let's pull ourselves out of the quantum realm before our heads spin right off and zoom back out to the molecular level. We're going to see how these incredible atomic interactions form the actual products we use every single day. Consumer chemistry is a massive field. It encompasses everything from the cleaning agents under your kitchen sink to the cosmetics and medicines on a pharmacy shelf. And modern chemistry isn't just mixing bubbling liquids in beakers anymore. It integrates cutting-edge advancements like nanotechnology and green technology to make products that are way more energy efficient and environmentally friendly. You know, you interact with this foundational chemistry in your diet too. We generally think of oils like palm oil and fats like butter as two totally distinct things, but on a chemical level, they are both simply esters. Yep, they are produced through the exact same esterification reaction between fatty acids and glycerol. The macro difference you actually experience, one being liquid and one being a solid, simply comes down to the microstructure of those specific bonds. Remember a few minutes ago when we talked about energy having to eventually appear as work or heat? Well, the potential energy, also known as enthalpy, possessed by all these consumer products, your food, your fuel, it's physically stored right here within their chemical bonds. When those bonds are broken during a chemical reaction, that stored potential energy is released right into our macroscopic world. Section 5, Understanding Interdependent Systems, the Big Picture. Finally, we have arrived at our last stop. We're zooming out to the ultimate macro level to see how all these scientific building blocks combine to form the complex world around us. To do that, we need to define what a system actually is. According to our sources, a system is a regularly interacting or interdependent group of items forming a unified whole. That means whether we are talking about a single biological cell, a rigorous food safety protocol at a huge manufacturing plant, or a massive global ecosystem, they all fit the exact same definition. They're simply made of individual parts working together. To really summarize the main concept of everything we've explored today, we have to adopt a systems thinking mindset. Systems thinking moves way beyond simple A causes B logic. It's realizing that component A doesn't just push component B. Instead, component B often feeds right back into component A, directly or indirectly, in highly complex, interdependent ways. The quantum particles build the atoms build the chemicals build the biology, and the biology interacts with the environment, all of it feeding back into each other constantly. As we wrap up this explainer, I want to leave you with the thought to really bring all of this home. Look around you right now. Think about the chair you're sitting in, the food you ate today, or whatever device you are watching this on. What complex, interdependent systems are you participating in today? I really hope this grand tour has sparked your curiosity about the incredible, interconnected scientific framework you live in every single day. Keep questioning, keep zooming in and out, and I'll catch you in the next explainer.